Hey, what's going on YouTube? It's time for another edition of Advent of Code. Real quick, on previous days, I missed day 8, Saturday night, Sunday morning, if you will. I had other priorities, so that was a night to rest. So I'm going to go over day 8 real quick. So day 8 was pretty straightforward. It was another grid problem. You had these antennas that were listed or throughout the map, and they all had some sort of letter or number denotion. Pretty much anything that was not a dot was an antenna. And we had to create the antinodes, which were essentially the a polar opposite, if you will, of half the distance to the center, basically, or twice the distance from each other. And so we could calculate that, and it's between any two antenna of the same type. So lowercase a's and lowercase a's, uppercase a's and uppercase a's, zeros, so on and so forth. And so we had to generate these antinodes. And once we generated them, we had to calculate the count of them. And an antinode could be on top of where an antenna already was. So what I did for my implementation for day 8 is it's day 9. For day 8, I just went through and made basically a map of antennas by the antenna type. So lowercase a, uppercase a, 0, whatever the letter map was, created those groupings. And then for each antenna grouping, I went through each set of antennas and then each set of the antenna again. And anytime, any, anytime the values would equal the same, meaning it was the same node, then I would just continue on to the next one. So that's pretty much how we accomplished day 1. If we were outside the bounds, if there was an antinode that was going to be created outside the bounds, we just continue. We don't count those. And then we calculate all those up into a map. We want the distinct set of where those antinodes were. So I stored them in a map, and then we return the length. That was pretty straightforward. Part 2 of day 8 was the same basic principle, except the antinodes could continue past just one iteration. And so as you can see here, like with T and T, you had antinode here, and then the T's themselves also became antinodes. So the way that we handle that is basically the same thing, but instead of just continuing, we just continue on the same trajectory, increasing our values of DR and DC from where the antinode is. As long as it's in bounds, we're good. And we do that until we get to the end, or until we're no longer in bounds. And then the last part of that was simply if it's a letter in the grouping, well, we know that that position is also an antinode. So I went ahead and did that grouping here as well. So that's how we accomplished day 8. Pretty straightforward, wasn't too complicated. I kind of did that off stream, but again, I had other priorities. So you end up with these values. And so we're now all caught up and we're moving on to day 10. The other thing I did off stream was I was talking about visualizing certain days. And so right now I have a way to visualize day 6. I'm kind of building a framework around these grids that, given a grid or that this kind of matrix mindset that I have, where we can visualize not only the inputs, but also the algorithm for the pathfinding. So this was day 6. I thought that was like one of the first ones that it would apply to. And so what you're seeing here is all of the places visited during day 6, part 1, as it's going through my input, and then eventually providing an output visualized here. Again, I'm building a framework around the matrix so that you can just provide some inputs and then it will do that as well. The interesting thing here too as well is that I didn't just do day 6 or part 1 of day 6. I also did part 2. So I'm just going to comment out that and do part 2. And so the difference with part 2 is obviously a little more complex, but with the visuals, what I did was we get back that set of visited nodes, and each one is either going to be a successful path or not. So I already know, I've already pre-calculated the successful path. So here, because it's a green color, or may look slightly yellow to you, that's a success. And then when we go on to the next iteration, we go ahead and try that again. I don't know if you can see it just faintly here, but this blue square, because there's so much data, it's kind of hard to fit on one screen. That blue square is the indicator of where I put the new iteration of the slice on the path. We would have stopped there on the path previously, but now we have that blockade. And so we're just getting started here and getting warmed up with a little bit of what I call pregame, get our juices flowing. Again, because this is green, we know that this one's going to be successful. It is going to reach the edge of the map, but this is every single iteration that we're going through here, obviously slowed way down, but so we can visualize it. And, you know, it's quite interesting to see what's going on here. So it's just some fun. You could find the matrix library that I put together in my GitLab repo. It should be listed in the links here. I'll list it on this video as well. But if you're interested in playing with this, I plan to extend it a little bit more so that we can visualize other Advent of Code days, not just day 6, but I'll be doing probably day 9. I think the defragment one will be interesting to visualize, and not only put these algorithms together, but kind of just visualize that data. You know, I've always kind of been a big fan of sorting algorithms, visualizing sorting algorithms. And so as we solve these problems, so here's an example of us getting into an endless loop. So the red here just indicates that we know that we're going to get into an endless loop here. We're not going to exit properly. I would like to update part 2 so that the green on here would just be where the looping is successful. And then only once it gets into the endless loop does it mark that red. And I think I could do that with some backtracking. But, you know, that's still also a little bit more advanced here. So, but again, this is just cycling through each of those possibilities. Now, part 2 had 1,909 different possibilities, possible iterations where adding a new barricade would cause an endless loop, I think is what the score was. So there's going to be a lot of iterations here, so we're not going to get through all those in this particular video, but this is something fun to play with at the beginning here, just kind of visualize what day 6 looked like. And I plan to go back and do more, but just kind of a start, and maybe I'll talk more about that on a different stream, but for now, this is just kind of something fun. As far as implementation goes, I try to make it pretty easy. I know this is, some people look at Advent of Code and they think in their mind, you know, they're doing it for competition. I'm not. I'm doing it to hone my skills and learn some new things. And so I built this matrix library or grid library that at some point, my wife is in the chat and she's distracting me. So, you know, but I do plan to update this library, but it's pretty easy implementation. I use that same matrix concept, and then, let me go to the actual visual. So I did create a separate function called visualize part 1, but that takes that same concept of the matrix, it plugs it into this display.new, and then you press in the matrix into that, and then from there you can you can do everything that you were doing previously, you can color them, etc. And then part 2 is the same thing with just some more complexity on coloring. So that app can run, but simultaneously the code can run in the background and then kind of fill in those visual aesthetics as we go. And so we're just looping through all of those possibilities. It's going to be a lot. What I did to optimize this, actually when I approached this particular day, is instead of putting a blockade on every single point in the map, I go through the visited list once and I only put a blockade on where we visited on that first iteration. That way, instead of testing every single point, I tested only points that we knew we were going to pass, since we were only putting one blockade there. Maybe it's a necessary optimization, didn't save a ton of time, but it just kind of was an approach of, if this map scaled to a much larger size, I know that I could spend less iterations, right? Get through it. So just some neat ideas. If you have questions on this, or if you have some thoughts, or just some feedback here, I'd be interested to hear it. We're getting ready for day 10. I mean, I could take a look at it at some point, Roni. I do quite a bit of code review right now at work in Golang. Actually, I write exclusively in Golang at work. I look at Golang on a pretty much a daily basis. And so, if that's something you're interested in, you can just PM me or send me your repository. And when I have some time, I'll take a look at it if you're interested. I'm not by any means going to suggest that I'm an expert or that I do everything idiomatically correct. But yeah, I might have some feedback for you. All right. So again, the red lines here are the ones that end or that we know have an endless loop, and the green ones are the iterations where we know we are successfully exiting. So this is just kind of something fun to do at the beginning here while we get warmed up. I'm going to go ahead and close this out though and get ready. Get ready for day 10. All right. 1 minute and 54 seconds left. Pictures coming together quite nicely here. I like how as you complete each puzzle, more and more is revealed. Not quite sure what we're looking at here. This looks like this might be a reindeer with a small Christmas tree on this side here, possibly. I'm not sure what's going on the left side and what this kind of channel is here in the center. But we'll see more as time progresses. Right. Any other questions before we get started here? All right. 1 minute left. Also looking, if anybody has any feedback on these videos or something they'd like to see more of, or just more of in general, whether it's specific tech topics or specific questions, maybe it's challenges, or, I don't typically do coding challenges on a regular basis, although I could say that everything that I do is a coding challenge. Maybe at some point I can speak more about what I do in my 9 to 5, but it's I think I do have quite a bit of knowledge in the tech industry, and would be willing to share on specific topics. Pretty much more on the back end side of things. I'm not so much a visual like front end guy. Don't push pixels, as they say, right? So, all right, let's dive into day 10. Day 10, hoof it. That was an accident. You all arrive at lava production facility on a floating island in the sky. As the others begin to search the massive industrial complex, you feel a small nose boop your leg and look down to discover a reindeer wearing a hard hat. The reindeer is holding a book titled Lava Island Hiking Guide. However, when you open the book, you discover that most of it seems to have been scorched by lava. As you're about to ask how you can help, the reindeer brings you a blank topographic map of the surrounding area, your puzzle input, and looks up at you excitingly. Perhaps you can fill in the missing hiking trails. The topographic map indicates the height at each position using a scale from 0 lowest to 9 highest, for example. Okay. Based on unscorched scraps of the book, you determine that a good hiking trail is is as long as possible and has an even gradual uphill slope for all practical purposes. This means that a hiking trail is any part that starts at height 0, ends at height 9, and always increases by a height of exactly 1 at each step. Hiking trails never include diagonal steps, only up, down, left, or right from the perspective of the map. You look up from the map and notice that each reindeer has helpfully begun to construct a small pile of pencils, markers, rulers, compasses, stickers, and other equipment you might need to update the map on hiking trails. A trailhead is any position that starts one or more hiking trails. Here, these positions will always have height 0. Assembling more fragments of pages, you establish that a trailhead score is the number of 9 height positions reachable from that trailhead via hiking trail. In the above example, the single trailhead in the top left corner has a score of 1 because it can reach a single 9. The one in the bottom left, this trailhead has a score of 2. Okay, so we've got a 0 here. We can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Okay. So if we're looking at this one, height trail is always 0. You establish that a trailhead scores numbers. Why is it the single trailhead in the top left corner has a score of 1? Because it can reach a single 9. Which one in the top left corner is it talking about? This trailhead has a score of 2. Okay, that makes sense. Oh, this one itself is a 9. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it. There's one other thing it said here. It has an even gradual uphill slope. For all practical purposes, means that a hiking trail is any path that starts at height 0 and at height 9 and always increases by a height of exactly 1 at each step. Okay, so it has to increase by 1 at each step. Got it. Okay, so that's 2. Got it. The positions marked are impassable tiles. To simply, these examples do not appear on your actual topographic map. This trailhead has a score of 4 because every 9 is reachable via a hiking trail except the one immediately to the left of the trailhead. Okay, wait a second. So we can't go to 9 here. But from here, we can reach this 9, 2, 3, and 4. Okay, so we can reach 4 9s from this single trailhead. This topographic map contains 2 trailheads. The trailhead at the top has a score of 1, while the trailhead at the bottom has a score of 2. Okay. So this is the one at the top. 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't go here because that's going down. We know we want to go gradually up. But this one can come all the way around here, and this one can go up here. Okay, I got it. Here's a larger example. The larger example has 9 trailheads. Considering the trailheads in reading order, they have scores of 5, 6, 5, 3, 1, 3, 5, 3, 5. Adding these scores together, the sum of the scores of all trailheads is 36. Okay. So I think we can so from this one, let's look here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Those are the same 8 and 9s. 3, 4, 5, 6, 7, 8, 9, 8, 9. Okay. Those are the same 4s. And then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Can it reach this 9? So the only thing I'm thinking about here is from a single trailhead, the number of distinct locations that it can approach, not just the total number. Because if I go right here, I think I can get to the same 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can get that way, and also 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can get to the same 9 twice from the same trailhead. It doesn't say how many zeros are in here. Let me check this input. So let's put this in our test file. And if I look for zeros, there's 9 of them. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this 0 here does count as a trailhead, even though it is in the middle of the map, which doesn't make a ton of sense to me. But I think that's the distinction, is that this one is 5, this one is 6, this one is also 5, and they're visiting the same spot for a given trailhead. So starting at position 0, it's visiting a unique set of points. Even if they can visit it from multiple paths, it's still the same unique set of 9s. And so we can get just the list of 9s because we have the different paths. And then as we get the list of 9s from the different paths, we can just you basically unique them, right? And then we can get that listing per a trailhead. So these are all numbers, and let me just check my input here. Yeah, so those are all numbers too. So we don't really have to do anything too crazy here. We can read this in as a using our matrix. So we can do a matrix dot new. Our in is the S, and then our separator is nothing, and we can do an as. We just do an ints. And so that should give us our ints here. Interestingly enough, that's fine. We'll copy that function if we need it. And then so if I would like to just get to walk through here first, and we'll just get all of our trailheads. So we'll just consider them as a list of ints, which is what I've been doing here. And then we can say for row in range of M. Be helpful if I sign that. And then for but actually we care more about yeah. And we do actually care about the value here, because yeah, so if b equal to 0, then trailheads equal to append trailheads. So that's just going to give us our trailheads, and I've said trailheads way too many times there in a row. And we're just going to take the row and column of that. So that's our starting position. So we know now that we can loop through each of these trailheads, and we can say, okay, call it trailhead. For each trailhead, we want to get back. We want to do something here. So we want to check up, down, left, and right. And we want to check each basically location to see if the current height that I'm at is 1 greater than If not, we don't return. And then if it's 9, I was a little unclear about that because what if we hit a pad of 9s? Each step has to increase by 1, so that doesn't matter. So I'm not going to worry about that at the moment. Actually, I don't think that's part of the solution here. At least I hope not. But we can recursively call this, right? And so we do, we'll just call it next, and we've got a so we've got our R and C, or our position, and then we've got our matrix, and we want to pass in our current value. Actually, it's part of the position. So what we can do is we can say and this is going to return a list of ints. So that'll be all of our positions, right? So anytime we get somewhere, we're just going to go ahead and increment that. And so for each of our trailheads, we're going to so this will be it'll be our position and our direction, right? So we can, from this trailhead, we can step from this position to what do we want to call it? Let's say, is it matrix dot? Yeah, matrix dot dir up, and we'll pass our matrix in. So we're going to step from trailhead, not position, and because we're at a trailhead, right, we're going to we'll just create a map of we'll just keep on this whole narrative of using maps here. So we'll call it trail ends, maybe. I don't know what you call a trail end. Does anyone know what you call a trail end? Is there like a word for that? Yeah, we'll go a string of that, and then we'll call it that. Actually, it's a slice of it, maybe. This will be our head, and then this will be the trails. Yeah, so we're going through Advent of Code, John. If you've never heard of Advent of Code, it's a 25 days of Christmas calendar of programming challenges. And so today is day 10. Every night at midnight you get a new puzzle dropped, and some people, they try to get on the leaderboards. I'm already not on the leaderboard. I'm sure somebody has done that already for today. But the idea is that you get a set of inputs in text, and you can choose whatever program you want. So in my case, I'm using Golang, but really it can be whatever choice you want. And you can solve those problems trying to come up with the outcome based on a certain set of criteria. So in this case, it's starting at 0, which is a trailhead, and then you're able to increment up by each level, and each number in that grid is considered a level. And you need to try to get to the number 9s, and then for each trailhead, count the number of 9s, and then sum up those totals. And so the first trailhead in here can reach 5 9s, the second can reach 6, so on and so forth. And that total for the test input is 36. But this is just the test input. Once we solve for that, the real input is this, which is a more complex problem. And every zero, not just the ones on the edge, have to be checked and tested, etc., etc. And so my initial approach is just going to be to go through these and get our unique sets and then come back and total all of those up for each trailhead. So I'm going to create, I'm going to do that, and so what we're going to do is we're going to append, we're going to say ends equal to append ends, and it's going to be to the step, right? And so what we're essentially saying is that for each step that we take, we're going to append those to the end of it. And we're going to do that for dir down, dir left, and dir right. Right. And then so our trail ends, make this plural, is going to be, yes, I do program in Golang on a regular basis. I prefer Golang. That is my language of choice. There are reasons for that. I've done quite a bit of work in Python in the past. Other languages like C#, some C++, some C, some PHP, a lot of PHP actually, JavaScript, somewhere around 17 years of experience in total. But I prefer statically typed languages, and so that's why Go is my preferred language of choice. I also really enjoy the concurrency model. So, you know, to me, yes, Go is my language of choice. Doesn't mean I'm amazing at it. It just means I'm good enough to get paid to do it. Yeah, so we're gonna go with this, and we're gonna do just what I typically do here, which is trailhead sub 0, trailhead sub 1. I guess I could shorten this by doing like %v or something for the stringified, but yeah, it doesn't really need to happen that way. So this is going to set in our map from what our trail head is, all the trail ends. So that's going to give us a distinct map. The one kind of issue here is we could have like duplicates in this set, but I think this is like a first kind of approach here. So we're going to do, I should dedupe this list realistically. That would be good. That would be good. So let's think about this for a second. I have these. Oh, I did use this step function. I haven't structured this out yet. So we're at a current position. So if my position 0, if my matrix position 0, position 1, so that's my current position. If my we'll go with our dir, because we always want up, right? We always want to increase. So we'll say minus our current position. It must equal 1, right? Then we're good, right? So if this is not true, if it's not equal 1, right, then we return. We'll just give it like an empty whatever. Otherwise, if it is true, right, we're going to check to see if our, oh, this is, this needs to be our current position plus this. Okay. So that's going to give us an index out of bounds problem potentially. So I'm going to do this, and we're going to guard against that. And so we'll change this to NR and NC. These are our new positions. It's just easier to reference it like that. And so the last thing we need to do here is .m.inbounds. All right, so we don't have that for ints. So let me go create that real quick. Yeah, should be easy enough. We'll come back to this later and clean this up. But for the purposes of this, we've got an I, we've got a J. Yeah, we'll call it that. It's fine. So what we're doing is we're just saying, are we inbound? And that will allow us to just create a nice little if dot inbound and nr comma nc. If we're not inbound, right, we want to return. So we want those nice little guard clauses here, right? So if not inbound, we return. Otherwise, what's the problem here? Oh, set input or div. All right, yeah. If it's not that, we return. If we're not incrementing by 1, we return. And we'll say if this equals 9, then we return. We just need to return this one location. So then it is NR NC. That's interesting. I guess I don't need to be a slice of int here. I'm only ever going to return just one position when we step, right? The only time it is ever going to be maybe in the next one, maybe we'll see. We'll see what it changes to. So okay, not inbound, we return not that. And if we are a 9, we return. Otherwise, we step again. And we need to essentially do this, right? So maybe we can collapse this down here in a minute. Maybe not. I don't know. But we'll just roll with it for right now. Okay. So any direction here, if we're not 9, could end up in multiple. So I do need to return a set of ints. I know if I get to the last one, it's only going to be 1. But it could be multiple from the step function. So right. Okay. Add these 3 dots back. Cool. Right. So the only thing I think that we're missing here is the deduping. So I think we are going to return multiple like ends here. But let's run the test. Let's start with a test and let's see what our difference is here for day 10. Declared not used. Oh yeah, okay, that makes sense. And all right, expected. That's not the right expected. The right expected is 36. So we can come back to our test and we can put 36 in here. I will just comment this out for now. Right. So I think what we didn't do is I'm getting the length of trailheads, which is really the length of all of the beginnings, but that's really not the score, right? It really should be, well, at minimal, it is going to be, let's do a score here. Call it that. And it's going to be score at minimal without removing the dupes. I know there's going to be dupes. It should just be trail ends once. Right, and then so this gets replaced with score. Okay, cool. Come back here. Actual is 0. Okay. Interesting. Okay. See what we got here. So we've got our map. We've got 0, 2 with an empty slice, empty slice, empty slice. Okay. So what do we have wrong then in our logic? So our new row is all in our new column is always going to be our current row and our current column plus our direction row, direction column. That's what I had wrong there. Okay. Let's give it another shot. Okay, 81. All right. So that's a little bit better. So then I think the last thing we have to do is actually like dedupe the trail ends per a set here. So for instance, we've got a trail ends for a given set of trail heads. And so I want to essentially ends equal to dedupe. I have this unique function. I wonder if this is going to work for that. Ah, beautiful. Cool. So now that we actually have the test passing, what this function does is it takes in a set and of int, and or actually I created it as a generic, a comparable type, but then it does a key map and then just kind of returns the values of that as a slice of the same type passed in. Just some helper functions that I built. So we've got that. Let me grab my puzzle input again. I don't remember if I stored it or not. And so we can actually see if we can run this thing somewhat efficiently here. So there's day that, and let's go back here. We'll run day 10 and see if it finishes in some sort of reasonable amount of time. 698. Let's get rid of that log message. So we come back here to day 10, and there we go. Perfect. That's the correct answer. Let me do a little bit of cleanup here. Get rid of this log message. Just make this a little bit cleaner. I think that's really the only one I had here. All right, let's dive into part 2. The reindeer spends a few minutes reviewing your hiking trail map before realizing something. Disappearing for a few minutes and finally returning with yet another slightly charred piece of paper, the paper describes a second way to measure a trailhead called its rating. A trailhead's rating is the number of distinct hiking trails which begin at the trailhead, for example, 0, 1, 2, 3, 4, 5, 6, 7, etc., etc. The above map has a single trailhead. Its rating is 3 because there are exactly 3 distinct hiking trails which begin at that position. Here is a map containing a single trailhead with rating 13. This map contains a single trailhead with rating 227 because there are 121 distinct hiking trails that lead to the 9 on the right edge and 106 that lead to the 9 on the bottom edge. Here's the larger example from before, and it's 81. That's funny. Okay, so that was the number that I got before I did the deduping. So I can literally take this out, go here, and then we're just gonna, copy, and we'll copy pasta, and we'll call it part 2, and we will get rid of the deduping, and then we'll get rid of this. And we will run our test and see if that, well, I guess I'll just run the input. Run the test pass. And so the inputs it's always the same actually from day 1 to day 2. But I am overly whatever. Yeah, exactly. Perfect. Wow. Well, there you have it. That's the right answer. You're 1 gold star closer to finding the chief historian. Knock that out. The approach I took here, I like organizing the data. I think we could actually just reduce it down to 1 function, and then on the part set, just do part 1, but then without the unique as opposed to the same unique. And maybe I'll clean that up here before I submit it. But stepping through kind of was the easy approach here. Maybe I'll visualize this one. Maybe I won't. But yeah, we got it knocked out. Does anybody have any questions? I mean, I know there's a couple people hanging out. So, feel free. Typically I spend a little bit more time on these things, but today I think went pretty well and got it knocked out pretty fast. What I was showing earlier today at the beginning, while I wait for questions, I am working on creating a library here where I can visualize some of these days. This is a snapshot from day 6 where I'm visualizing the routes that we took with the path checking on day 6. I may apply something similar here to day 10 and kind of see what we can do as far as visualizing the different steps we go through to get to the optimal pathing. at least get those distinct ratings, etc. So, but this what this is showing is anything that's red is what was described on day 6 as something that ends up in an endless loop by adding a new blocking condition. And so this is just a way to visualize the algorithm. It's obviously slowed down quite a bit just to allow you to get some visual aesthetics here, but it's pretty fast as far as that goes. So we can it's just going to keep going through all the different iterations. And I think it's a pretty cool just perspective on what it looks like for the algorithm to kind of walk through its pathing and things like that. So we'll apply that more as we go. I'm going to end the stream here tonight though and redeem some of the time. I thank you all for joining me. If you have any questions, please feel free to comment. If you like this kind of content, please like and subscribe. I like to produce more of this. I find this entertaining for myself, and hopefully, you find it interesting as well. But thank you for your time, and as always, you have a good night.